Starting recording. I am in the recording. Your voices are not in the recording, and I noticed actually yesterday the voices were not in the recording either. But that's because I kind of started all of a sudden and I didn't do all the checks. So, yeah. Can someone say something? Okay. Yes.
Hello.
In the recording. We're good. Is
Yay.
the text on the bottom of the screen correct?
Yes.
Did I do that right? Hopefully. There should be one
5
space.
to 6. And then you have one at 8, right? 8 to 10?
Yes, exactly. Well, 8 to when. Yeah, I mean, I probably won't go later than. No, I won't go later than 10. Whoops, I should fix the. There. Good. I won't go later than 10, but yeah, probably.
Yeah, that means to get those 10 hours of sleep, eh?
I gotta. Yeah, I mean, yes, I have to get sleep before I do a test.
You actually get 10 hours of sleep, like consistently?
I don't get
or-
10 hours. No, I don't get 10 hours sleep, but I try to sleep as much as I can.
Wait, how much do you sleep usually?
Not as much as I want. Like last night I got good sleep. Last night I slept 8 hours, 8.5 hours.
Isn't 8 like what you? I think 8 is like what you're supposed to have at this age.
Yeah, well, maybe 10, really more, but I mean, I think everybody could use 10 hours of sleep, but we don't get 10 hours of sleep.
Sleep should you have at
Okay,
18?
you do that research, Erwin. I'm gonna start. I'm gonna start the questions here. So yeah, okay,
8,
yeah.
8 and 10 per 24 hours. Between
Yeah.
8 and 10.
So there we go. I guess I was okay. I feel okay today. So, should we start with? I feel like, okay, we can start with this lab question, this tutorial question. It's just that I don't really know how to do it that well. So hopefully, maybe some people can help, or we can just figure it out together. It's a weird question that took some time to figure out when I tried to figure it out the first time. So let's start here. But if we don't make much progress, maybe let's try some other questions first, and then we'll go to this. So can everybody see the question?
Yes, as you can see the question.
Okay, so in the arrangement shown below, an object is hung from a string with that linear mass density that passes over a light frictionless pulley. Okay, the string is connected to a vibrating object which vibrates up and down with the frequency f, so that's the vibration frequency. The length of the string between the point P and the pulley is L equals 1.5 meters. When the hanging mass of the object is either 16 or 25 kilograms, standing waves are observed. No standing waves are observed with any mass between these values. What is the frequency that it's vibrating at? Ah, thank you, Fatima. Yes, good. Thank you for sending that. Okay, good. We have solutions. So let's start here. Well, what do we know? So we know linear mass density is 0.002 kilograms per meter. I know basically the tension, right? Because this is the force of gravity, that's the force of tension. So I know the tension is the mass times g. Okay, so I know the speed of the string now, which is good. I'm looking for F, that's our target. Okay, target. And I know the length of the string is 1.5 meters. Okay. And what I also know is that when I put on a mass of 16 kilograms, that gets me some nth harmonic. And when I put on a mass of 25 kilograms, that gets me the n plus 1th harmonic. Does that make sense? That gives me the next harmonic up from it. So the actual value of the frequency is the same, because the frequency is the frequency, right? It's just the frequency of the machine that's running. That isn't changing. It's the mass that we're putting on top. That's what's changing. Or the mass that's like changing the tension in the string. So let's see. How do
you know that they're consecutive? Like consecutive harmonics?
Because no standing waves are observed with any mass between these values.
Okay.
Right? That is what tells me it's the next harmonic, right?
And since it's heavier, don't we expect one down? Because it's heavier? It have more tension?
Yeah, that might make sense, because I remember when I did this before, I got a negative value for some reason. So yeah, a negative value in the wrong spot. Quite possibly. So we have more tension. If we have more tension, that means it would be the lower harmonic. No, I think if it had more tension.
No, it would be the lower, because it would be moving faster. So it means it would have less peaks. If the wave is moving faster through the string,
yeah,
it peaks less because it's like there's less of it.
Okay, so the other way around here, or it would be n minus 1?
Yeah, n minus 1.
n-1 harmonic. Okay, that makes more sense than what I had before. So, okay, what am I looking for? Frequency f. Well, okay, something we know is that fn, first of all, fn equals fn plus 1, because that frequency isn't changing. Right? That's something we know. I also know that fn is n times v over 2l, and I know that fn plus 1, or fn minus 1, sorry, it's minus 1. fn minus 1 is n minus, and I really got plus 1 in my brain. N minus 1 times v over 2l. Then, what are we looking for? We're trying to solve for either f's here. So we got to figure out which harmonic it is. That's what the first thing. We got to figure out which harmonic it is. So in a sense, we need to solve for n here. I can take the ratio. Yeah, this will work. I can take the ratio of these two equations. So fn over fn minus 1 equals n. I can't write nv over 2l over n minus 1 v over 2l. This ratio is 1 because they're the same, right? So this implies 1 equals n over n minus 1, right? Or n minus 1 equals n, and now I'm stuck. Yeah, what'd you say? The v's are different. The v's are different. Yep. Also because I got n minus 1 equals n, which it gives me negative 1 equals 0.
Wait, why do we use n minus 1 and not n plus 1?
Why do we, sorry, what'd you say?
Do we use n minus 1 and not n plus 1?
We used n minus, why is the question?
Yeah, why?
Because when the tension increases, so if the tension is like this for Fn, and we're increasing the tension, right? What that means is that the wave is going to go through the string faster, which means the next harmonic is going to have less peaks, which means it's going to be a lower harmonic. So when you tighten it, when you tighten the string, what that means is that we have lower harmonics.
Okay, thank you.
Because the wave is going to go through faster. Right?
Is Fn the 6th harmonic? Because on the string there's 6 curves.
That would make sense, except that that doesn't get you the answer for some reason. Because you don't know what mass this is. Not for some reason. Because you don't know what mass this is. If we were told that that was the 25 kilogram mass, then I think, is that 6? That's 6. I think even then it's not even the 5th, and it's not even the 6th harmonic that's being used. I think the picture is just not helpful here.
Okay.
But wait, how do you know the frequencies are the same?
Because the machine just has one frequency. The machine is outputting with frequency f. It's not a frequency depending on the mass. It's always the same frequency.
So no matter what, Fn and Fn minus 1 will always be the same.
Yeah, they'll be the same.
Where's this from? Is this from the tutorial?
This is from tutorial, yeah. Am I recording?
Yeah, it's from tutorial.
Check if I'm recording. Yes, I am. I do that too often. So what we can do now is that, I missed one thing here, which is that the v's are different, right? So this is vn, and this is vn minus 1. So, what cancels? We do have this, but this is then going to be vn over vn minus 1 there, right? That's what we missed. That is still a ratio of 1 there. So now I can say, I'll still say 1 equals n over n minus 1. Vn is the square root of the original tension over the linear mass density. That didn't change, right? So I can, the tension over the linear mass density. And then here, similarly, it's the n minus 1 tension over the same linear mass density. So, we know this will cancel. So the linear mass density is constant. 1 equals n over n minus 1. So this is just going to be the square root of m, so the first mass, I'll call it m1g, over the square root of m2g. Right, so and just to be clear, this is m1, this is m2. Right, m1 and that. Okay, now we can solve for n, because we know everything except n here. So it will be, I guess I just have to, what do I have to do? I have to take it out and then multiply, or let's just see. N minus 1. I guess I just have to say n minus 1 root m2g equals n root m1g, and then multiply it in and then isolate. Yeah, okay, that'll be fine. So n root m2g minus n root m1g plus, equals root m2g, and then just isolate for n. So n equals root m2g over root m2g minus root m1g. There. Okay, so plugging everything in, and this should be a whole number, and it was when I did it before. What'd you say, sorry? Oh, I can cancel the g's. Is that what someone said? I can cancel the g's. I realize. So this is actually just root m2 over root m2 minus root m1. And, well, this is the square root of 25 over the square root of 25 minus the square root of 16. Thankfully, these are all nice numbers. Right? So this is 5 over 5. So this is 5. So we get that n is 5. So it actually is the 5th and 6th harmonic that I got. So n is 5. Never mind. It's the 5th and 4th harmonic. What that means is that this first one, this m1, is giving us the 5th harmonic, and this m2 is giving us the 4th harmonic. Right? So now I think I can just plug in either 4 or 5 to here with the correct mass, and it should work. Yeah, so let's get this. So I got so we're talking about the 5th harmonic now. So I know that the 5th harmonic will be 5v over 2L. Okay, it's going to be 5 times the square root of the tension over the linear mass density over 2L, which is going to be 5. Sorry, that's a 5, not an S. Square root of, so M, so this is for the 16 kilogram, right? So M1. Yeah, M1 times G over the linear mass density over 2L. My writing is getting bigger and bigger as we go left to right, of course. So let's try this. 5 times the square root of M1, which was 16 times 9.81, not 9.84, 9.81, over mu, which was 0.002 over 2 times 1.5. 1.5 is the length of the string. So I got that the 5th harmonic frequency, F5, which is F4, is 467 hertz. And is that the right answer? Yes, it is.
Yes, it is the right answer.
It worked.
And
Can I just quick grab a screenshot of the question?
The question? Yeah. It is also in discussions, but yeah, here it is.
Oh, I'll grab it from you then.
Okay.
I'm using M1 because you found Fn, not Fn minus 1, right?
Yeah, I found n, right? I know I could have used, I think, let's check if I could have used that, because I remember this was actually something from before that was causing trouble. Let's see if I chose Fn minus 1, so F4, right, because n is 5. So if I use 4 and use the correct, so M2G over mu over 2 times L, let's see if we get the same number, because we should. And if we don't, then that's weird. So that's going to be 25 times 4. And I get the same number. Good. I also get...
Yeah, you get the same number.
I get 467 hertz. Which makes sense, because the frequencies are the same. Right? I set up here, Fn equals Fn minus 1. So that would be weird if I got not the same number here. But I did get the same number, so we're good. Okay, good. I'm happy I could do that. So, any questions about this? I'll quickly recap, even if nobody has questions, because I'm sure it's confusing. What we had to do is we had to figure out which harmonic they're talking about, right? Because I could solve for n, I could solve for f, I mean, if I knew what harmonic they were talking about. I can't just assume because I don't know, and I mean, we're not supposed to look at the picture. I would think we would look at the picture, but I just know that that's not the answer by looking at the picture. So you had to actually solve for what the harmonic is that they're talking about, which is n. So I used the fact that we know these two equations, right? And we know these two facts are true with their corresponding masses, right? Because this mass M1 corresponds to Fn, and this mass M2 corresponds to Fn minus 1, because it's a lower harmonic, because it's a tighter string. And so, yeah, and so what we got here is the ratio is 1. I just solved for n because I knew v, vn, and v minus 1, just making sure you take into account the fact that vn and vn minus 1 are different because of the different masses, although L is the same. And solve for n, I got exactly a whole number 5, which is good, which is telling me that n is the fifth harmonic. So I can just solve for the frequency now, but knowing that it's the fifth harmonic, right? Which is what I did down here, knowing that it's the fifth harmonic.
Will there be like a question where like we would have to round, where it's like where it gives us an answer of like 4.98, and then we'd round to like a fifth harmonic?
I don't know. Although if I got 4.98, I would round to 5.
But they would not give you a question where an integer doesn't come out to be an integer. I don't think.
Yeah. No, they wouldn't do it. But it could, just because of math, right? Just because of typing in numbers into a calculator. It could, but no. Most likely, it will give you a whole number. I wouldn't imagine they have. Yeah.
Can you say the number B?
Yeah, we're gonna do B still. Yeah, there's still. I see it. It's on the screenshot you sent.
Thank you.
No problem. So. What is?
Sorry.
Yeah.
I just gotta cut you off because I can't watch the stream because there's a max number of viewers.
Oh yeah. Okay.
So
I thank you for telling me that. I will fix that.
Damn the mods.
By the way, could you scroll up a little bit?
Yeah. Oh, sorry. That wasn't a little bit, was it? Here.
Yeah, like in the middle. Yeah, right there. Thank you.
You can watch me for that.
Oh, thank you, Erwin.
Of course.
Oh,
Can you guys
Oh,
see
is
me?
Manuel here? Is Manuel here now?
no, if everyone's doing it, it's fine.
Okay. There we go. Good. I was just about to message in tutor chat. There you go.
I was already here, massively. But can you guys see off my screen?
Yeah, but there is a bit of a delay, sadly.
I think that's normal, isn't it?
Is there a delay when Manuel does it?
So I hear your voice, and then I don't hear the voice, or I don't see your mouth move until like 2 seconds later on his stream.
Yeah, that is.
I'm having that while watching.
I'm watching
Adam's
Adam's stream, and I have that too. Just
Oh, really?
Oh,
Yeah.
Oh, I didn't know that. I didn't know that.
Don't worry, Adam. It's okay. As long as you can see the writing, it's okay. Because it's a second. It's not.
I guess
it's
so.
not big enough.
Yeah. As long as
Yeah.
you can still follow along. I think I have pretty okay Wi-Fi. So like I'm on Ethernet. So I think it probably is Discord that's causing the trouble. But
Yeah. By the way, does it echo when I ask a question or no?
I don't hear it. But maybe they hear it.
The viewers, do you guys hear it?
Whoever's watching Urban stream, just mute the stream so you just hear Adam.
Yeah. Mute Erwin stream. Yeah, that's right.
And then I can ask a question if I need to.
Mhm. I'll still hear you.
Because can't you hear Adam regardless of if you're watching the stream or not?
Yeah, as long as they'll be listening to me but watching your stream. So if they can mute, they can just like right click your video stream and mute it.
Yeah, let me just make
if
it
it's a
put
double.
one. There you go.
Okay. Question before I move on to part B. Any questions? No? Okay, then I'll move on to part B. So part B is asking, what is the largest hanging mass for which standing waves could be observed? So, okay, so every time you add a mass, it is getting lower and lower in the harmonics, right? Every time you add a mass, because it's getting tighter, and you're going to eventually get to the first harmonic. So what we're essentially looking for is F1, which is the same frequency as before, is 1 times V over 2L. Or just V over 2L. So the first harmonic is the lowest harmonic, right? So we want to know what mass causes this. So in other words, mg over mu over 2L. And we just solve for m here. And that will be the largest mass that will get us the first harmonic. And any mass bigger than that will not get us any harmonic. And any mass lower than that will get us some nth harmonic or nothing.
Well, wait, how do you know that every time the mass, you get a mass, like, is it just like because of the first question, or is it something like a rule?
No, I just know because of the situation. So as you add mass to this, right, the string is getting tighter. What that means is that the speed of the wave is increasing through it, and that means you're going to get lower and lower harmonics. So the next harmonic, well, maybe not the next one, but you get something like that, and then eventually you have the first harmonic, which would just be that. right? Which would be,
And I want to ask, so in this, like, in what question does it apply when, like, you have to, like, the harmonic goes from like 1 to 3? Like, what is that with like closed ends and open ends?
yeah, that's with a pipe. That's with a pipe. If you go to the first to the third harmonic to the fifth harmonic, that's with a pipe. Yeah.
Ah, okay. So like, if it's just a string, then it's just like 1, 2, 3, 4, whatever.
Yeah. There's all integer harmonics for strings. Yeah.
But with the pipe, one of the sides would have to be open, right? And then the other side would have to be
Yep.
closed.
Yep. One is open, one's closed for that.
It's like some rules. Like if it's like one of them is open, one of them closed, it's like one.
A node and then an antinode, right? Something like that.
Yep. It's well, we'll get to that. We haven't done that yet, but yeah, we'll get to that.
And we're assuming this whole time that the frequency is remaining the same, correct?
Yeah, because the machine's only giving one frequency.
Okay, good. Yeah.
Right. Yeah. The machine's only giving one.
Yeah, because that's how that assumption can be made, actually. The higher mass, the lower fundamental frequency.
Yeah. The higher the mass, the closer we're getting to the fundamental frequency.
Yeah. Closer.
Right.
Yeah.
Okay, so I think it's supposed to be m, not n. But there you go. We just plug this in. So 4 times 1.5 squared times 467 squared times 0.002 over 9.81. So I got that the biggest mass that we can get is 400 kilograms.
Oh, I got that swap. That was way too high.
Is that right? Well, it's supposed to be a big mass, so...
No, yeah, that is correct.
Yeah, there we go. Okay, so any questions about part A or part B of this question? It was a good one. We did it before, right? We didn't fully get the answer, but we got it.
You just did it like on your own. It's like we didn't do it like here, so that's good.
Yeah, exactly. So we're good now. Let's see. Any questions about this one?
Okay, you know what? It's not a question, but it's more of a statement that I want to make.
Okay.
That I didn't realize until later on that really helped with me understanding this question.
Mm-hmm.
If you ever had a cord or of some sort and you pull it tighter, and then it starts to vibrate and its frequency rises much faster. It's hard to explain, but if you pull the cord, it starts to the frequency at which it oscillates is much faster, and that's because the tension is rising. But I made the assumption thinking that for question B, where it talks about, sorry, can you scroll down so I can read it? What's the maximum? Yeah. What's the largest hanging mass for which the standing waves could be observed? So I made the assumption that the frequency would have to increase the heavier the mass became, but that's not the case in that example. Because I applied the real life example where if you pull on a cord, the frequency rises, but in this case, that's not the case. Rather,
because the machine has a single frequency. The machine has a single frequency. Yeah.
So just in case anyone who doesn't yet understand that, that's
good. What's going on. Makes sense.
Yeah, I guess isn't you have to either if you want to keep the frequencies the same, then you have to either trade the tension or the n. So one of them has to go anyway. So,
well, V equals lambda F, right? So if I'm bringing this up. Oh, well, I guess I should say V over lambda equals F, right? So if I want this to stay the same, right? If I want this value to stay the same, and I'm bringing this up, if this value is getting bigger, I want the total value to counteract and get smaller. So I want to bring this value up as well. So lambda has to get bigger. Am I doing that right? Hold on. Let me make sure. Let me think. This is getting bigger. Yeah. This is getting bigger. Yeah, this will stay the same if it's proportional. Right? If I have twice the speed and twice the lambda, if I want to keep it the same. But, so what's happening here is that the speed is increasing, so the wavelength is increasing, so we have a longer thing. Instead of it being, something like this, the wavelength is getting longer, right? And so that's why, since we know the frequency is constant, and this is what's changing, so that means that the lambda has to get bigger. And that's why, as you increase the tension, the harmonics go down instead of going up for a set frequency.
Yeah, you explained that much better than me. Good job.
Oh, don't worry. Yeah, this work together. We work together.
I'm to those for a reason.
Okay, so I got another question in the chat. This one, and let's give it a try. So in this problem, ignore any motion of the moon around the Earth. Oh, this is okay. So this is a gravity problem, but okay, sure. We can. This is going to be the first. The gravitation.
No, this is perfect. This was the example I was stuck on right now.
Yeah.
Let's
yeah.
go.
Well, that's because you sent it in the chat. That's why I have it right here.
Oh,
so there you
really?
Go. Yeah.
Oh, awesome.
There you go. So you work for a company which wants to place a satellite of mass 10,000 kilograms at a point between the Earth and the Moon so that it feels no net force. How far away from the center of the Earth must you place the satellite so that it feels no net force? Okay. So in this problem, ignore any motion of the Moon around the Earth. Okay. So we just have.
By the way,
yeah.
We're given a list of constants at the beginning of this tutorial.
Okay.
I'll send that to the group.
Could you? Yeah. Could you? Thank you. So this
I
is.
think I know how you solve it. Can I take my guess?
Sure.
Okay, so the way I'm guessing it is you just have to like do f that the between the moon and the satellite has to equal between E and the satellite, and you just have to like do algebra.
Yeah, that makes sense to me. This is.
You need the radius between the Earth and the Moon, and then you just say the radius. Like one distance is going to be the radius of, like the radius between the Earth and the Moon minus x, and the other one would just be r.
Yeah.
No, it'd be the full radius minus r, and the other one would just be r.
These two distances. This distance here is then L minus R, or L minus R here.
Wait,
right?
Does it not? Well, why does it matter that the moon's behind it though?
Because it could work as a counteractive force to make sure that F net equals 0. Because if the moon wasn't there, then the satellite would just fall down. So there would be a net force on it.
Well, what we know is the sum of the forces equals 0. Okay. So what are the forces acting right here? Well, we have a gravitational force this way, right, towards the Earth, and we have a gravitational force this way. So I'll call that Fg2, and this is Fg1. So I'll just define that as positive. So then we have that Fg1 is equal to Fg2, right? And now what are these forces? What are the forces that are acting here? Well, we have, that's that. Let me find my notes quickly. My notes are also still in homework help. They're pinned, so you can find them there. If you
Quick question. Are we gonna, like, for the radius of the Earth, mass of the Earth, do we come with that ourselves? Like, Google it and write it down, or are they gonna give it to us?
They probably will give it to us. No, they'll give it to us on the test, but for right now, we can just Google it.
Okay.
Right. Okay, so the magnitude of this, the magnitude of this is G times the thing causing the gravitational field, which is the Earth, over the radius from it, which I'm calling r squared. That's our target variable, right? Then, does it give us the distance between the Earth and the Moon?
I think it's like 230.
Yeah, there is.
It gives us in the question?
Yeah, so D equals 3.84 multiplied by 10 raised to the power of 8. It's right there. I sent it, I believe.
Oh, okay. Then I'll find it after. It's okay. Thank you.
Okay. Yeah, it's all there.
Yeah, thank you. So G over the mass of the Moon over, so this is going to be L minus R squared, right? This distance, L minus R squared. L is that total distance. L minus R is the distance between the satellite and the Moon. R is the distance between the Earth and the satellite. And I have one variable, one unknown, assuming I know the mass of the Earth, the mass of the Moon, the distance between the Earth and the Moon, I can just solve for R.
Well, don't you have to include the mass of the satellite is 10,000?
That's what I was going to say, yeah.
You have to include the mass of the satellite?
Because we're trying to find the force.
Oh, you're trying to find the force. You're right. Yeah, you're right. So, yeah. So it's just the mass of the... It does cancel out, yeah. So the mass of the satellite and the mass of the satellite will have to be... Because now it's a force, but I guess they do both. They cancel out on both sides here. So now, because the force is the mass times the acceleration, right? So, or mass times the thing. Wait, hold on. Does that make sense? Yeah. Okay, so I technically did this a little wrong, but I'm not going to get the wrong answer. My logic was just a little, like my use of the formula was a little wrong. I should have done that the absolute value of the force of gravity is Gm1m2 over r squared. But I'm essentially using that. I just kind of used it in a backwards way. So I did it kind of like mass times acceleration. This is the mass times acceleration. Mass times acceleration. The masses cancel. I shouldn't have really done it like that, but yeah. So, applying this here, we get the same equation. So now I just solve for r. So I'll flip both of them or it doesn't really matter actually. So I'll just say G M E times L minus R squared equals G M M R squared. I will get a quadratic out of this, of course. So it's going to be G. Oh no, I have to square that. So G M E. So this is going to be L squared minus 2LR plus R squared equals, G M M R squared. Then multiply everything in. So L squared G M E minus 2L R G M E plus R squared G M E equals G M M R squared. Yeah?
Yeah, instead of doing this, I think it would be better if you like not expand the quadratic and just take both the squares on one side and then square root the other side.
Yep. That would have been better. But I'm here. I'm here now. I'm almost almost done. But yeah, that would have been better for sure.
Yeah.
Okay, so I'll just keep going for now then. I think that's the only thing that doesn't have an R, so that's a constant term. The rest of them have R's in the way we want. So the R squared term is G M E minus G M M. The R term is just minus 2 L G M E. Yep. And then the other term is minus L squared G M. Oh, hold on, but I have to. Sorry, I forgot how to solve a quadratic. Plus L squared G M E. Okay, and I just plug this into my calculator.
I got a question.
You can cancel G's before you do
that. I can cancel G's, yep. So factor G out of here, factor G out of here, well, you don't have to factor it there, but yeah, G's do cancel. Good, and then I just have R squared M E minus M M plus R minus 2L M E plus L squared M E equals 0.
And aren't these all constants, so it's not even that much quadratic solving?
What'd you say? Sorry?
Like, aren't there all constants? Because like we know M E, we know M N, and we know L, so it's just like...
Yeah, it's just plugging this into a calculator, yeah. It's just, we don't have to do any more calculations. Polynomial degree 2. So the first one is ME. I'll find those numbers in the chat. So mass of the Earth is 5.97 times 10 to the 24 minus mass of the Moon, which is 7.35 times 10 to the 22. So that's my coefficient there. Minus 2 times the length. L is Earth-Moon distance. Yep, 3.84 times 10 to the 8.
That's what I want to ask you about. For that L value, do we include the radius of the Moon and the Earth on top of that L value, and then minus it from the radius of the satellite to the Earth?
No, well, L is what we need for this part of the equation. But what's the exact wording of the question? How far away from the center of the Earth must you place? So it's all from the centers. We don't have to worry about radius.
Well, because that 3.84 multiplied by 10 raised to the power of 8 doesn't accommodate for the radius of the Moon. I don't think, at least.
You don't think so?
Yeah, because it just says the distance from the Moon and the Earth, so maybe they didn't accommodate for like the radius of each of the planets. So that's why I thought maybe
Why would it accommodate for Earth, but wouldn't accommodate for the Moon?
I would assume first that they did account that's accounting for the centers. Those are the distance between centers. And if there was a problem, and if we don't get the answer, that is somewhere that there could be.
What's the number that they gave?
3.84 times 10 to the 8.
They did account for it.
So that's to the centers. Those are the differences between the centers.
That is from the centers. I just searched it up.
Okay, sounds good. Then there we go. 3.84 times 10 to the 8 times 5.97 times 10 to the 24, which is the mass of the Earth. I'm plugging this all in one go. I hope if the number gets weird, then let's see what happens. So L again is going to be L squared, so something squared times the mass of the Earth. So the thing squared is 3.84 times 10 to the 8. Oh, these are all meters and kilograms, I hope. I think so.
Yeah, everything is meters and kilograms.
Okay, sounds good. 97 times 10 to the 24. Okay. So my answers for R are 431,925,338.2 meters, or R equals 345,647,798.4 meters. And I think both are right. I don't know. I don't know which ones, how I would choose which one's right or wrong. I would.
Is it like?
Isn't the one that has 4 further away than the? Like it's 4. It's this 431,925,338.
Oh, it's like past the moon.
Further away than the radius.
I think it's past the moon. It's like, wait, how many decimal places? 1, 2, 3, 4, 5, 6, 7, 8.
So it has to be.
Yeah. So it's the bottom one. This one is still right. It still would have a net zero force. It's just that it's past the moon where it has a net zero force.
No,
Here
it
is.
wouldn't have a net zero force past the moon. They'd both be pulling in the same direction.
Oh yeah, you're right. That's true. That doesn't make sense.
It's just because it's a quadratic equation. So
I guess so. Yeah. What would that other point be? Yeah, they are both pulling in the same direction. And yeah, I don't really know. Or it could be, no, I don't know. Anyways, this is definitely the answer though, because it can't be that top one. So that's the answer. And is that the answer to the question?
Yeah, again, it is. It's 3.46 multiplied by 10 raised to the power of 8 meters, which is the bottom one. But why again can't it be the top one? You said that it goes beyond the radius.
It's bigger than L. This is greater than L. So
Because
L is that distance.
Oh, I see. Yeah. Or
So
else you would get a
it's
negative.
over here somewhere, right? And it doesn't work. The answer wants it between the Earth and the moon.
Yeah, why would you put a satellite like after the moon? You know, like it doesn't make sense.
It doesn't make sense. That would be hard to communicate with.
Unless you're Elon Musk.
And also, the question doesn't want that. So. Okay, so there's that one. That's good. That was our first gravity question. But did that make sense?
By the way, if you didn't do all of this quadratic stuff and just plugged in numbers from like the third-ish, oh, you had to get the R out anyways. Okay, never mind.
I had to get the R's out. Yeah, exactly.
It's mostly an algebra question, right? It's just like you just have to know how to move things around, but it's not that difficult.
Yeah, it's just sort of all of the physics questions are how do you set it up, and then how do you solve for the variable you need to. That's kind of all the physics that we do right now. So yeah, how do you look at the question, set up some equations that lets you solve for the variable you want, and then solve for the variable you want. That's the physics.
When I tried solving this question, I went straight into the values, and I didn't end up canceling out the mass of the satellite, even though it could.
Yeah.
But I mean, so I'm not too sure why, but my final quadratic does end up with imaginary values. So the degree. So you see how our variables are.
Yeah.
For r squared, I have it as a positive sign, and then for my constant, it also has a positive sign, so that it indicates that the parabola is above the x-axis, and it's not gonna ever cross the x-axis. So there's no solution. So I just want to know, when it comes to solving these sort of questions, would it be? It's probably suggested just to sub in your values last.
Yeah. Yes. Sub in your values last for sure. It's you do that because you don't have any rounding errors, right? You also sort of get a more understanding of how the physics works, like how the actual variables are related to each other, and you can check your units pretty easily at the end. If you know you just see the variables, you know what each variable represents, so you can check your units pretty easily. Numbers would be harder.
I see.
Because you have to remember what units, or you write the units with it, but it's easier just to write a variable. So yeah. Okay.
Numbers are too big anyway.
Numbers are too big anyways. Yeah, I wouldn't do it. Okay, so there's that. I mean, I don't have any more questions in the chat, so I will continue with textbook questions. But yeah, if anybody has more.
Oh, do you have the questions now, or are we still on waves?
Let's finish waves, I think. We don't have to do every question. But Yeah, we're in the additional problem section of waves. So maybe since we're in the additional problem section of waves, maybe let's move on to gravity, and finish the do gravity. Does that make sense? Sounds
Well, we
like
do have 10 minutes left, so let's get one question done, then we can go to the study session.
okay. Then let's
Yeah.
let's do one question of waves, and then we'll do the gravity
Okay.
stuff all after. Yeah.
Fair enough. Then we'll start on a clean slate.
Clean slate after.
edit.
Yeah. And we'll finish off the interference stuff if we have time after at the end. So 34. 34? 34. Two strings are vibrating at the same frequency of 150 hertz. After the tension in one of the strings is decreased, an observer hears 4 beats each second when the strings vibrate together. Find the new frequency in the adjusted string. Okay, so not bad. This is a little too easy. So the beat frequency is the absolute value of the difference between the 2 beats, right? So initially, they're both at 150, right? What happens after, and so you have a beat frequency of 0 because the difference is 0. What happens after is that F2, the tension in F2 is less than the tension in F1, right? So if you're decreasing the tension, that means it's going to get looser. So let's see what happens. Let's see. Remember, V equals F lambda. V is the square root of T over mu. Mu is a constant. We want to see how F changes when T changes. So as T goes up, T is going down, this value goes down. So I guess lambda is the wavelength. What's happening with the wavelength? I don't really know. I'm trying to decide how does F go. I think F is supposed to, so you're decreasing the tension. So I think F is supposed to go down. You're supposed to have a lower frequency. But how do I show that? F is going to go down because the lambda, I think, oh yeah, for some reason, I remember this from a lab actually, lambda will stay constant in this situation. So since lambda is staying constant, this value is going down, F has to go down. Although I don't really have, yeah.
Lambda's 2 pi over k. K is a different, it's a wave number. It's independent.
Okay, yeah. Lambda is 2 pi over k, and k is not changing because k is part of the wave structure, I guess. So yeah, I remember that lambda was staying constant. So if lambda stays constant, then F has to decrease. So the lower frequency is what we care about. The frequency is going to be lower because remember, absolute value is going to give us 2 answers, and we only take the lower one. So, our new F beat is 4 beats per second. So FB equals the absolute value of F1, which is 150 hertz, minus F2, which I know I already said that, but I'm just going to say F1 here is 150 hertz. And we're solving for F2. 4 beats per second. Oh no, I just solve for F2. That's it. So I just say the observer here is 4 beats, so 4 equals the absolute value of 150 minus F2. And now I just say, well, there's 2 options. 4 equals 150 minus F2, or 4 equals 150 minus 150 minus F2. Right? So either F2 equals 146, moving that over and then subtract, 146, or F2 equals 154. And so it's this one. Because again, we take the lower one because frequency has to go down.
That's it?
That's it?
Someone confirm that though, because I'm assuming that because K is part of the wave equation, it's like lambda is independent, but I actually have no way of confirming that.
Yeah, I'll look it up. I'm gonna copy and paste the question into Google and see if we get an answer.
Do you have Chag, Adam, or something?
Sorry, what?
Do you have Chag?
I don't have Chegg, but I just looked up the question and that is the answer. So yes, we're good.
Wait, sorry, can you go back to the question again, like the?
Wait, why we picked the smaller one again? Did it say in the question that you decreased, one of the strings decreased?
The tension in the string decreased, so since the tension decreases, the frequency has to go down.
Yeah, okay, yeah, I get it. Yeah. I didn't read the question. Thanks.
Yeah, no problem.
And this is different from the other one because in the other one the frequency stayed the same, but the n changed. But this one's like different.
Yeah. Okay, I will start the next question. We'll see if we finish it. Probably will, actually. So 35 is... sorry, is there any more questions for 34 before I move on? Good? Okay, I think we're good. So 35 says... The ship in this figure travels along a straight line parallel to the shore at a distance d, which is 600 meters from it. The ship's radio receives simultaneous signals from the same frequency from antennas A and B, separated by a distance L equals 800 meters. The signals interfere constructively at point C, which is right there, which is equidistant from A and B. The signal goes through the first minimum at point D, which is directly outward from the shore from point B. Okay? Determine the wavelength of the radio waves. Ooh, okay. There's a lot of information here. So, right here, the waves are coming. And at exactly this point right there, they constructively interfere. Right? So, we're going to have to find that length, I'm pretty sure. But once we find that length, we can use... give me 1 second. I will find the equation. Here. Constructive interference occurs for these ones. So if the distance between the absolute value of the difference between the distances that the waves have traveled, which is this, is n lambda, for any positive integer lambda, for any positive integer n, then that's constructive interference. Okay, I should have included the thing that says constructive. Destructive is for n plus a half lambda instead of n lambda. So we know that this is true. We know that the absolute value of the difference between these two, right, is n lambda. And for... I don't know for what n, but I think that's why we have to find this here. So that's why it doesn't matter. Okay, so let's find this r first. I'll call this r1. Actually, I don't have to draw a line. I'll call this r1. I'll call this r2. So let's try to solve for r1. Well, this length over here is 600 meters. This length over here is 400 meters. So that length is r equals r1 equals the square root. It looks like r1 equals r2 as well. Because that would be 600 and 400. Yep, so r1 equals r2 equals the square root of 600 squared plus 400 squared. So that's going to be the square root. Oh, they're going to be the same, so that's going to be 0. Whoops. They're the same. So
Does
0.
that mean that n is 0?
I guess so.
It's 0 with multiple of lambda?
N equals 0. So, yeah, we don't have to do any math here. This is going to give 0 equals n lambda. Lambda isn't 0, so n is 0. N equals 0. So, although maybe I should have said including 0 here, but
why not use point D?
Yeah,
Yep.
I think you're supposed to use point D because it's destructive interference there, because then it's lambda over 2, and I think it would be
Okay.
and the radius will be different. I think.
the radius will be different there. So let's give it a try. Let's see what happens. This is for the destructive interference that happens at point D. Right? First signal goes through the first minimum at point D, which is I'm pretty sure that means destructive interference. So now we need to find whatever these. So that doesn't matter anymore. Now this is our R1, and this is our R2. So the absolute value of the difference between the two, so what's the first one? Well, this is 800 meters, and that's still 600 meters, and that's still 800 meters. So first of all, R2 is 600 meters. R1 is, well, it's just going to be the square root of 600 squared plus 800 squared. Okay, so square root of 600 squared plus 800 squared. So 1,000. 1,000 meters. So the absolute value of the difference is 400, which is equal to n plus 1/2 lambda. And since I know that n is 0, I can just say this is lambda over 2. So lambda equals... Maybe? Is that the answer? I don't know. Let's see. Since I got from up here n is 0, then 400 equals lambda over 2. So 800 equals lambda. Let's see if that's the answer first, and then I'll decide.
That is the answer.
That is?
Yeah.
Okay, good.
I think I did this one before. It's Springer's starting, so if people
Yep.
want to hop over to that.
That is the answer, so we're good. Yeah.
Oh, where did you get the 400 from? I'm so confused.
Quickly before I start explaining, yeah, anybody going to Springer now, go to Springer. I will be there in a few minutes. I'm going to start again when he's done. Give me like a few minutes after he finishes. I'll say something in tutor announcements when I'm starting. And we'll continue after with textbook questions and any questions from the chat. So enjoy that. Enjoy the lesson with Springer. Okay. Oh, and perfect timing, my headphones died. Oh no, they don't die. They just go offline for some reason. So give me 1 second. 2 seconds. And can someone say something? Nope, don't hear it. Give me 1 second.
Hello?
Yep, I hear it now. Good. So, any questions? Yeah, about this one?
Yeah. Where'd you get the 400 from exactly?
This formula here?
No, like down there where the 400 equals. Yeah, there. Where'd you get the 400 from?
Oh, that's this. That's this, right? Because R2 is 600 and R1 is 1,000, so the difference between them is 400, and that's equal to n plus 1/2 lambda. But since I said from up here that n is 0, right? Oops, that's too far. Since I said from up here n is 0, right? N equals 0. That gives us that, and we can just solve for lambda now.
So for this...
Wait, go ahead.
Yeah, I just want to know, why did we assume that n was equal to 0 for both cases, where they're connecting at 2 different points?
I don't really know what n is. What is n? It's just some multiple?
Yeah. So what... I mean, couldn't n be another value?
Yeah, I think it could. Yeah, it could. I don't really have an explanation for that. I got n equals 0 here. I put n equals 0 down here. I don't really. Yeah, n is just some multiple. It's not like a harmonic because this is before we did harmonics. So, yeah, I don't really know. Yeah, it seems like it could be a different integer. Yeah, go for it.
Isn't it because it's the first minimum though? That's why n is 0.
Oh, maybe. The first minimum. Yep. The first minimum.
Meeting is being recorded. Question was, what is the interference at point D?
Yeah.
Comparing this is R1 and R2 from the source.
All right. Okay. Yeah. No, that makes sense then. First minimum at point D.
Yeah, that's good. Okay, guys. Well, go to Springer, and I'll talk to you. I'm gonna go to Springer now too, and I will talk to everybody afterwards. Okay. So, bye everybody for now.